Good evening, fellow physics learners. As I was reviewing the problem set number 5, in particular this question, which concerns a car stopping at an intersection, it became apparent that a number of us were having difficulty with this solution to this particular problem. So let's go over it here. Um, First things first, we'll sketch the situation. Here's a car speeding down the road. Your art really doesn't count for much, so don't worry about that. As you can see, mine's not too great. Car's moving down the road at a positive velocity of 20 meters per second. That's the initial velocity in the x direction. We know it's coming to a stop, so the final velocity in the x direction will go to 0. But since we know this problem is going to involve Newton's second law, because we're asked to determine the friction force applied by the brakes to stop the car, what we actually should be doing is converting this particular picture or sketch to a free body diagram, like we did in the previous problem. Let's take a look here. What we do is we basically separate the vehicle, the object, from its environment, and just apply all the forces that are acting on the vehicle. The first force which comes to mind is the force of gravity. So it's acting straight down. And we'll label that in a second here. Let's see, that's the force of gravity, which is equal to the mass of the car times the acceleration of gravity. What other forces are acting on the car? Well, there's the normal force acting by the road onto the car at the tires. That's going to, since there's no acceleration, no movement in the vertical direction, the normal force will effectively be equal to the force of gravity. Well, what other forces are acting on this car? Well, person applies the brakes to the car. There's a friction force which is going to act on the tires. Unfortunately, I've got that to run in the wrong direction. So let's cancel that. Actually, I can do it by flipping it left to right. And so that friction force is the opposite of direction motion. We're going to call that the friction force, F for force, subscript little f for friction force. And I believe that's the free body diagram of the car, the only forces acting on that car. And all the action that we're concerned about is in the horizontal direction, the x direction, and the only force acting on that car in the x direction is the friction force. The velocity the car had when it was going down the road, just as the person was applying the brake, was due to the energy that the car had by the tires doing work on the car and the engine and giving it some kinetic energy. But once that kinetic energy was reached, there was no longer a force acting on it, on the car, until the individual started to apply the brakes. Okay, so now we're going to apply Newton's second law. The sum of the forces in the x direction, since that's where all the action is equal to the mass times the acceleration in the x direction. Translating this to what we have on this free body diagram, we have a friction force. And since it's in a negative direction, I'll put the negative in there. You don't have to do that. It should come out negative if you don't actually force it that way, is equal to 1,000 kilograms, which is the mass of the car, times the acceleration in the x direction. Well, we have one equation here with two unknowns, and we have to figure out what one of the unknowns is before we can solve this. And it appears that we have enough information to solve for the acceleration of the car in the x direction. What is the acceleration of the car in the x direction? By definition, it's the change in velocity of the car in the x direction over the change in time. Another way of stating that, it's v final minus v initial over delta t. We know that v final is 0 minus v initial is 20 meters per second all over delta t of 5 seconds. And we come up with an acceleration of negative 4 meters per second squared. We can then take that number that value, and plug it in for the acceleration. We have the friction, also effectively plug it in here as well, actually, that the negative friction force is equal to 1,000 kilograms times negative 4 meters per second squared. And since the units are all in the SI standard units of meters, kilograms, and seconds squared, this will come out in newtons, and that answer is equal to 4,000 newtons, pointing in the left or negative direction. Basically the solution to the problem. If you have any questions, by all means drop me a PT or a general discussion thread. Thank you very much.